Judith Basin, Montana. February 1891. When 63-year-old Matthias Corver announced he'd build his new cabin on top of his livestock barn, the ranchers of Hanson's trading post didn't hide their laughter. "Swede's gone soft in the head," muttered Tom Bradley, a cattleman who'd survived 18 Montana winters. "Heat rises, sure, but living above your own stock? That's desperation, not engineering." But Matthias wasn't desperate. He was calculating. What this Norwegian immigrant understood about thermal physics would save him over 2 cords of firewood that winter, while his neighbors burned through their supplies and still woke to frost on their cabin walls. His floor stayed warm enough to walk barefoot at 2 a.m., even when outside temperatures plunged to 23 below zero. They called him crazy, until winter proved him brilliant. Before we reveal exactly how Matthias turned animal heat into an all-night heating system, hit that like button and subscribe, because by the end of this story, you'll understand a frontier engineering principle that could cut your heating costs in half. Drop a comment telling us where you're watching from and whether you've ever heard of barntop cabins before. Let's dive in. The design seemed absurd on paper. Matthias planned to construct a 16 by 24-foot cabin directly on top of his existing barn structure. Not beside it, not attached to it, on top of it. The barn housed 6 dairy cows, 4 horses, and roughly 30 sheep during winter months. Animals whose combined body heat most ranchers considered wasted warmth that simply rose into the rafters and vanished into the Montana sky. "You'll suffocate from the stench," warned James McCall, who'd built 11 cabins across the Judith Basin. "Ammonia from that much livestock will blister your lungs. And the weight. Your barn wasn't built to carry a whole cabin." Matthias listened politely. Then he showed McCall his calculations. The existing barn had been overbuilt from the start. Massive 12 by 12-inch corner posts of larch, with cross beams every 4 feet. Matthias had designed it 3 years earlier with exactly this expansion in mind, though he'd told no one. The structure could easily support another 4,000 pounds. His cabin would weigh roughly 3,200. As for ventilation, Matthias had a plan that made McCall shake his head. "You're going to freeze yourself trying to avoid the smell," the builder predicted. But Matthias wasn't worried about cold air. He was counting on it. What Matthias understood was this. A single dairy cow produces between 1,500 and 2,000 BTUs of body heat per hour. 6 cows, 4 horses, 30 sheep. He was sitting on a living furnace generating roughly 18,000 to 24,000 BTUs hourly, all winter long, whether he harnessed it or not. That heat was currently escaping through gaps in the barn roof, warming nothing but snowflakes. The question wasn't whether the heat existed. The question was whether he could capture it, filter it, and transform his floor into a radiant heating surface that would hold warmth through the night. By mid-September 1891, Matthias began construction. His neighbors gathered to watch what they assumed would be a spectacular failure. Tom Bradley placed a bottle of whiskey as a wager that Matthias would abandon the project before first snow. "No man," Bradley announced, "can live above his own barn without going mad from the smell or freezing from the drafts you'll need to stay sane." Matthias smiled and kept building. He had 4 months until winter. And he had a secret that 18 centuries of Scandinavian farmhouse builders had proven worked, even if Montana cattlemen had never heard of it. The physics were elegant. The execution required precision. Matthias didn't simply drop a cabin on top of his barn and hope for the best. Between the barn's ceiling and his cabin's floor, he created an 18-inch air gap, a thermal buffer zone that would become the heart of his heating system. Here's what most people miss about rising heat. It doesn't rise forever. Hot air rises until it meets resistance, spreads horizontally, and if you design the space correctly, transfers its thermal energy into whatever mass surrounds it. Matthias intended that mass to be stone. The barn's original roof came off. In its place, Matthias laid a platform of rough-cut planks, sealed with rendered sheep fat, mixed with ash, a traditional Scandinavian weatherproofing technique that created an airtight barrier. On top of this base, he positioned river stones, each roughly 8 to 12 pounds, collected from the Judith River over the previous 2 summers. These weren't decorative. They were thermal batteries. 4,300 pounds of sandstone and river rock, laid in a matrix 18 inches deep. Above this stone layer, another plank floor, the surface he'd actually walk on. But between the stones and his walking floor, Matthias left strategic gaps, narrow channels, 4 inches wide, running the length of the cabin in a grid pattern. These channels would allow heated air from below to contact the underside of his floor directly, while the stone mass absorbed and radiated heat constantly. You're building a Swedish contraption nobody's ever heard of. Observe Elizabeth Corver, Matthias's daughter, who'd come from Helena to help. What if it doesn't work? Then I'll have a very expensive stone floor, Matthias replied. But it will work. Your grandfather heated his house in Ringerike this way for 40 years. The principle is older than America. The ventilation system was equally calculated. Matthias installed 4 adjustable vents in the barn's walls, 2 on the north side, 2 on the south. Cold, fresh air entered low, near the animals. Their body heat warmed it. The heated air rose through carefully positioned gaps in the sealed platform, entered the 18-inch buffer zone, flowed around and through the stone mass, and finally vented through adjustable outlets on the cabin's roof. The genius was in the flow rate. Too much airflow, and the heat escaped before the stones absorbed it. Too little, and ammonia built up. Matthias calibrated the vents to create a gentle, continuous circulation, enough to keep air fresh, slow enough to maximize heat transfer. James McCall visited in late October, when the cabin was nearly complete. He stood inside, studying the floor. "This is either the smartest thing I've ever seen," he said slowly, "or the most elaborate way to freeze to death ever devised. You've got no firebox, no stove, just rocks and animal breath." "I have a firebox," Matthias corrected. He pointed down. 6 cows, 4 horses, 30 sheep. They eat hay. They make heat. The heat doesn't disappear. It goes where I tell it to go. McCall left shaking his head. But 3 months later, he'd return to study every detail. Because by January, Matthias Corver's barntop cabin would be the warmest structure in the Judith Basin, heated entirely by livestock, retained by stone, and costing him nothing but the hay he was feeding his animals anyway. Not all stone is created equal. Matthias knew this. Limestone, abundant in Montana, was his neighbor's default choice for foundations and hearths. It was readily available, easy to split, and adequately fireproof. But limestone has a specific heat capacity of roughly 0.22 BTU per pound per degree Fahrenheit. Sandstone, on the other hand, clocks in at approximately 0.24, a seemingly trivial difference that becomes profound when you're working with 4,300 pounds of thermal mass. Matthias chose sandstone deliberately. Over a 12-hour night, that extra 0.02 BTU per pound per degree translated to roughly 200 additional BTUs stored in his floor, enough to maintain a perceptible temperature difference when outside temperatures hit the extreme lows Montana was famous for. But the stone's composition was only part of his strategy. The arrangement mattered even more. Traditional masonry hearths store heat in a vertical mass beside or behind a fire, efficient for radiant warmth in one direction, but limited in coverage. Matthias's design distributed thermal mass horizontally across his entire living space. Every square foot of his floor was a heating panel. Walk from one corner to another, and you were always standing on stored heat. The stones weren't simply piled randomly. Matthias laid them in deliberate patterns, with larger stones, 14 to 20 pounds each, positioned in the center where airflow from below was strongest. Smaller stones filled the perimeter. This gradient created differential heating rates. The center absorbed heat faster during peak animal activity hours, evening feeding and night, while the perimeter stones, slower to heat, retained warmth longer into the morning. Between the stone layer and his walking surface, Matthias installed a secondary buffer, 1 inch of compacted clay mixed with straw, a technique he'd learned from his father. This clay layer served 2 functions. It distributed his weight evenly across the stone matrix, preventing pressure cracks, and it acted as a final thermal regulator, smoothing out temperature fluctuations. His walking floor itself was 2-inch thick pine planks, tight-fitted with minimal gaps. Pine has low thermal conductivity. It doesn't suck heat away from your feet the way stone or metal would, but it's thin enough to allow radiant heat from below to pass through. Stand on Matthias's floor at midnight, and you felt warmth. Not scorching heat, but the gentle, consistent warmth of sun-baked stone in late afternoon. "How hot does it get?" asked Carl Haugen, a Norwegian neighbor who understood what Matthias was attempting better than most. "The stone itself reaches between 90 and 110 degrees Fahrenheit," Matthias explained, "depending on how cold it is outside and how tightly I close the vents. The walking surface stays between 75 and 85, warm enough to be comfortable. Not so hot you can't stand on it barefoot." The thermal mass did something else, too, something Matthias hadn't fully anticipated but came to appreciate. It damped temperature swings. When he fed the animals at 5 a.m., their activity and fresh hay consumption caused a burst of additional heat. In a conventional cabin, this would spike room temperature, then drop sharply. But Matthias's stone floor absorbed the surge, released it gradually, and maintained remarkable temperature stability. His cabin rarely varied more than 6 or 7 degrees over a 24-hour cycle, even when outdoor temperatures swung 40 degrees between day and night. By November, the system was complete. Matthias moved in, arranged his furniture, and waited for winter to test his engineering. He didn't have to wait long. January 14th, 1892, 4:30 a.m. The thermometer outside Matthias Corver's barntop cabin read 23 degrees below 0 Fahrenheit. Inside Tom Bradley's conventional log cabin, 2 miles east, frost patterns decorated the interior walls despite a fire that had burned all night. Bradley's wife, Sarah, woke with a wool blanket pulled over her face, her breath visible in the lamplight. Inside Matthias's cabin, the temperature held at 68 degrees. He woke that morning, placed his bare feet on the pine floor, and felt warmth radiate up through his soles. No fire in a stove, no coals to tend, just the steady, reliable heat of 4,300 pounds of sandstone that had absorbed the body warmth of his livestock throughout the night and was now releasing it, exactly as he'd calculated it would. The cold snap had arrived suddenly. January 12th had been a manageable 12 degrees Fahrenheit. By the 13th, temperatures plummeted. Wind from the north brought Arctic air that turned spit to ice before it hit the ground. Ranchers across the Judith Basin burned through firewood at alarming rates. Conventional wisdom said you needed a roaring fire in your stove from sunset to sunrise just to keep interior temperatures above 45 degrees. Matthias didn't light his stove at all. He did make adjustments, closing his ventilation openings to 3/4 their normal width, reducing heat loss while maintaining just enough airflow to prevent ammonia buildup. Below, in the barn, his livestock clustered together, their combined body heat rising through the sealed platform, swirling through the 18-inch buffer zone, saturating the stone mass with thermal energy. At 6 a.m., Matthias went down to feed his animals. The barn interior measured 34 degrees, cold enough to see his breath, but 27 degrees warmer than outside. The animals were calm, their winter coats fluffed, but not stressed. He forte into their mangers, checked water troughs, and returned upstairs. By 7 a.m., neighbors began arriving. Tom Bradley came first, ostensibly to check on Matthias's welfare. "Wanted to make sure you hadn't frozen," Bradley said, stamping snow from his boots. Then he stepped inside and stopped. "Jesus, Mary, and Joseph. It's warm in here." 68 degrees, Matthias confirmed. "Would you like coffee?" Bradley walked the perimeter of the cabin, touching walls, examining the floor. "You've got no fire going." "None." "How is this possible?" Matthias explained the system, the stone mass, the rising heat, the calculated ventilation. Bradley listened, then asked the question that would define the next month in the Judith Basin. "How much did you burn last night?" "None," Matthias replied. "I haven't lit the stove in 4 days." By noon, 7 ranchers had visited. By evening, the story had spread to every homestead within 20 miles. The old Norwegian who'd built a cabin on his barn was staying warm through the worst cold snap in 15 years without burning a single log. The mockery turned to fascination. The fascination would soon turn to replication. If you're finding this valuable, hit that like button and subscribe, because what happens next reveals why traditional knowledge isn't primitive, it's proven. Drop a comment. Would you try this design in your own homestead? The cold snap lasted 11 days. When it finally broke on January 23rd, Matthias had burned approximately 1/8 of a cord of wood, and that was only for cooking and occasional backup heat during the absolute coldest hours. His neighbors, in conventional cabins of similar size, had burned through 2 to 3 full cords during the same period. The math was undeniable. The engineering was sound, and the mockery had permanently transformed into respect. February 3rd, 1892. Tom Bradley stood in Matthias Corver's cabin with a notebook, pencil, and a determination to understand exactly what he was witnessing. "Walk me through the mathematics," Bradley said. "Not the theory. The actual numbers." Matthias obliged. Over the previous 3 weeks, he'd kept meticulous records, a habit ingrained from his years as a ship carpenter in Christiania before immigrating to Montana. The data told a story that transformed skepticism into replication. Temperature differential. During the January cold snap, when exterior temperatures averaged -15 degrees Fahrenheit over 11 consecutive nights, Matthias's cabin maintained an interior average of 66 degrees. That's an 81-degree difference between inside and outside, sustained without conventional heating. Tom Bradley's cabin, by comparison, with a fire burning continuously in a standard cast-iron stove, managed an average interior temperature of 52 degrees, a 67-degree differential, achieved only through constant wood consumption. Matthias's system provided 14 additional degrees of warmth while consuming 0 firewood for heating purposes. Wood consumption comparison. Bradley had burned 2 3/4 cords of split pine during those 11 days, roughly 550 cubic feet of wood. Matthias burned 1/4 cord, and that was entirely for cooking. For heating alone, the comparison was stark: 550 cubic feet versus 0. Even accounting for the full winter season, September through March, Matthias estimated his total heating wood consumption at 1.5 cords. Bradley would burn 11. That represented a cost savings of over $40 in wood value, nearly 2 months' wages for a hired ranch hand. Over a decade, the savings would pay for an entire new barn. Heat retention duration. This metric fascinated Bradley most. At 10 p.m., when the animals had settled for the night and were generating steady baseline body heat, Matthias's stone floor measured 96 degrees Fahrenheit at its warmest point, directly above the main livestock area. By 6 a.m., 8 hours later, that same spot measured 84 degrees. A 12-degree drop over 8 hours, with no additional heat input beyond what the animals naturally produced while sleeping. Bradley did the calculation in his notebook. 12 degrees divided by 8 hours equals 1.5 degrees per hour heat loss. His own cabin, when he let the fire die at midnight, lost approximately 7 degrees per hour. Matthias's thermal mass was retaining heat nearly 5 times longer than conventional construction. But what about spring and fall? Bradley asked. When it's not cold enough to need this much heat? Matthias had anticipated the question. I adjust the vents. More airflow means less heat retention. In September and April, I keep all 4 vents fully open. The stone barely warms, maybe reaches 70 degrees. Comfortable, not hot. In deep winter, I close them to 1/4 open. The system self-regulates based on how much heat I allow to accumulate. There was another number that impressed Bradley, though Matthias mentioned it almost as an afterthought: structural efficiency. The barntop cabin design eliminated the need for a separate foundation, separate walls, and a separate roof for the living space. By integrating the cabin with an existing structure, Matthias had reduced his construction material costs by an estimated 30 to 40% compared to building a standalone cabin of equivalent size. You're telling me this saves money to build, costs nothing to heat, and stays warmer than anything else in the basin, Bradley summarized. Why isn't everyone doing this? Because it requires thinking like a Norwegian farmer instead of an American rancher, Matthias replied. In the old country, We lived above our livestock for 1,000 years. Not because we were poor, because we were practical. Americans think anything old must be backward. Sometimes old just means proven. Bradley closed his notebook. I'm rebuilding my barn this summer, he said, and I'm putting my cabin on top of it. I'll need your help with the stone calculations. Matthias smiled. You'll be the second. Carl Haugen already asked me last week. By next winter, I expect we'll have 5 or 6 barntop cabins in the basin. In 10 years, it'll be standard practice. He was wrong about the timeline. It happened faster than that. By March 1892, 3 ranchers had begun planning barntop cabin construction. By September, actual building was underway on 4 separate homesteads across the Judith Basin. Tom Bradley's design came first. He followed Matthias's specifications almost exactly. 18-inch air gap, 4,100 pounds of river stone, adjustable ventilation. The only modification was the addition of a small auxiliary stove, not for primary heating, but as backup during the most extreme cold and for psychological comfort. Bradley's wife, Sarah, wasn't yet ready to trust livestock as her sole heat source. Carl Haugen, the Norwegian neighbor who'd understood Matthias's plan from the beginning, built the most ambitious version. His barn housed 8 milk cows and 6 horses. More animals meant more BTUs. Haugen increased his stone mass to 5,200 pounds and expanded his cabin to 20 by 28 feet. He also incorporated a design element from his childhood in Trondelag, a secondary thermal battery in the form of a soapstone bench that ran along one wall, positioned directly above the warmest section of the barn. The bench absorbed heat during the day and radiated it at sitting height all evening, a heated seat that his family gathered around after supper. James McCall, the builder who'd predicted Matthias would freeze or suffocate, surprised everyone by being the third to commit to the design. I was wrong, he admitted publicly at Hansen's Trading Post. And I'm not too proud to learn from a Swede, even if he's actually Norwegian. McCall's version incorporated one innovation. He used limestone for the perimeter stones and sandstone for the center, creating a dual-mass system where the faster-heating sandstone responded quickly to evening heat while the slower limestone provided all-night retention. By winter of 1892 to 1893, 7 barntop cabins were occupied in the Judith Basin. The results were consistent across all designs. Interior temperatures 60 to 70 degrees, with consumption reduced by 70 to 90% for heating, and most importantly, families staying genuinely warm through Montana's brutal winters without the constant anxiety of feeding fires through the night. The social shift was profound. What had been mockery 18 months earlier became a source of regional pride. When ranchers from neighboring counties visited, Judith Basin homesteaders would proudly show off their barntop cabins, explaining the physics of thermal mass and rising heat with the confidence of engineers. The technique even acquired a local name, Corver heating, though Matthias himself insisted on calling it Old Country sense. Not every attempt succeeded perfectly. Olaf Jensen built his cabin atop a barn that housed only 2 cows and 4 sheep, insufficient animal mass to generate adequate heat. His family spent a miserable December before he admitted defeat and bought 4 more cows. The problem wasn't the design, it was undersizing the heat source. Another rancher, Michael Cleary, tried to save money by using only 1,200 pounds of stone. His floor warmed adequately but couldn't retain heat through the night. By 3 a.m., interior temperatures had dropped into the low 50s. He spent the following summer hauling another 2 tons of river rock to bring his thermal mass up to proper specifications. These failures actually strengthened the overall adoption. They proved the system wasn't magic. It was engineering. Get the ratios right and it worked. Cut corners and it didn't. The precision required forced builders to think carefully, measure accurately, and respect the physics involved. By 1895, an estimated 23 barntop cabins existed within a 75-mile radius of the original Corver homestead. The design had spread through demonstration, conversation, and the undeniable evidence of families sleeping warm while burning a fraction of the wood their neighbors consumed. Matthias Corver, now 67 years old, had become an unlikely consultant. Ranchers would ride to his property with sketches and questions. How thick should the clay layer be? What if I only have limestone available? Can this work with a horse barn, or does it require cattle? He answered every question patiently, never charging for advice. Knowledge that keeps families warm shouldn't cost money, he'd say. Besides, you're all proving me right. That's payment enough. What Matthias Corver built in Montana in 1891 wasn't an invention. It was a resurrection. The practice of housing humans above livestock for mutual thermal benefit traces back millennia across multiple cultures. In Norway, the Sakalt, or byre-dwelling, tradition placed living quarters directly above cattle barns as early as the Viking Age. In the Alps, similar designs existed in Switzerland and Austria, where alpine farmers called them stockley. In Scotland, Highland crofters built longhouses with humans at one end, cattle at the other, and heat flowing between them through carefully designed openings. Even outside Europe, parallel developments emerged. Traditional Korean homes sometimes incorporated ondol heating systems combined with livestock shelters, using animal warmth as part of a larger thermal strategy. In parts of rural China, particularly in northern regions, communal buildings placed human sleeping platforms above animal quarters during winter months. The principle was universal because the physics were universal. Mammals generate heat as a metabolic byproduct. Heat rises, and thermal mass stores energy. These weren't folk superstitions. They were engineering solutions developed through centuries of cold climate survival. So why had this knowledge largely disappeared by the late 19th century in America? Several factors converged. First, the availability of cheap wood in newly settled territories made fuel-intensive heating seem practical. Why bother with complex thermal mass systems when you could simply burn more logs? Second, American building traditions, imported primarily from England and Germany, favored separated structures, barns separate from house, each with its own foundation and heating system. This separation was partly aesthetic, partly based on fire safety concerns, and partly cultural preference for spatial division between human and animal spaces. Third, and perhaps most significantly, was the association of old country methods with poverty. Immigrants who'd lived above their livestock in Europe often saw the practice as something to leave behind, a marker of hardship they were eager to transcend in the New World. Building a separate house, even a less efficient one, signaled prosperity and assimilation. Matthias Corver's genius wasn't in inventing something new. It was in recognizing that old didn't mean inferior. He looked at Montana's climate, calculated the thermal resources he already possessed in his livestock, and applied a solution that had kept Norwegian families warm for generations. He thought like an engineer, not a status seeker. The broader lesson extends beyond heating systems. Traditional knowledge, whether in agriculture, construction, food preservation, or resource management, often represents accumulated empirical wisdom refined over centuries. Dismissing it as primitive usually reveals not the limitations of the knowledge itself, but the arrogance of those doing the dismissing. Modern off-grid enthusiasts and homesteaders are rediscovering many of these principles. Passive solar design, thermal mass heating, root cellars, and integrated animal systems are all experiencing revival among people seeking energy independence and connection to older, proven methods. What was mocked as backwardness in 1891 is now celebrated as sustainability in 2025. Matthias Corver lived in his barntop cabin until his death in 1909 at age 80. He never paid for heating fuel. His floor stayed warm every winter night for 18 years, powered by nothing more than the animals he would have kept regardless. The cabin still stood as of 1923, when local historian Margaret Fielding documented it in her survey of Judith Basin pioneer architecture. Whether it survives today is unknown, but its influence certainly does. Every modern home with radiant floor heating, every passive house design that maximizes thermal mass, every building that integrates natural heat sources rather than fighting them, these all echo the same principles Matthias demonstrated on that Montana ranch. He proved that sometimes the smartest innovation is simply remembering what worked before we forgot it. Before you go, hit that like button if this story changed how you think about traditional building methods. Subscribe for more forgotten frontier engineering that still works today. And drop a comment. What old technique do you think modern builders should revive? Let's keep this conversation going. The ranchers laughed at the old Norwegian who built his cabin on top of his barn. But when winter came, they weren't laughing. They were learning. And that's how wisdom survives. Not through books or schools, but through cold nights, warm floors, and the humility to recognize that our ancestors weren't fools. They were survivors. And their solutions, tested by centuries of necessity, still have much to teach us. Educational note. This documentary script presents historical building techniques for educational and historical interest. Any construction project should comply with modern building codes, engineering standards, and safety regulations. Consult qualified professionals before attempting experimental heating or construction systems.